Meta unveils breakthrough research, decoding human thoughts into text with 80% accuracy in real time using non-invasive brain-computer interfaces. Date: February 14, 2025. Overview. Meta, formerly known as Facebook, has made significant strides in brain-computer interface technology, presenting groundbreaking research from its fundamental artificial intelligence research Fair Lab. The research focuses on decoding human thoughts into text with an impressive 80% accuracy in real time through non-invasive techniques. This innovation could revolutionize communication for individuals with speech impairments such as those suffering from ALS or brain injuries. Key findings. 1. Breakthroughs in decoding brain signals. The research, conducted in collaboration with the Basque Center on Cognition, Brain and Language, reports two main breakthroughs. The first breakthrough is an AI model that converts brain signals into text utilizing non-invasive methods like magnetoencephalography (MEG) and electroencephalography (EG). This model successfully decodes up to 80% of characters typed by participants, demonstrating a significant improvement over previous technologies. The second breakthrough involves understanding how the brain transforms abstract thoughts into structured language. Researchers uncovered a dynamic neural code that connects successive representations of thoughts, words, and actions, providing new insights into the hierarchical nature of language processing in the brain. 2. Potential applications. The primary aim of this research is to aid individuals with speech loss by developing non-invasive brain-computer interfaces. The findings could lead to new methods for restoring communication abilities in patients affected by conditions such as ALS, brain injuries, and other neurological disorders. The hierarchical processing of language in the brain revealed through this research may enhance AI systems, making them more adept at understanding and generating human language. 3. Collaboration and support. Meta's commitment to neuroscience is underscored by its partnerships with various research institutions across Europe. And the company has announced a $2.2 million donation to the Rothschild Foundation Hospital to support ongoing research in this area. Detailed insights. 1. Methodology. The study involved 35 healthy volunteers who typed sentences while their brain activity was recorded using MEG and EEG. The AI model was trained to reconstruct sentences solely from these brain signals. The results indicate that the AI could decode characters with high accuracy, outperforming traditional EEG methods. However, the need for participants to remain motionless in magnetically shielded rooms presents practical challenges. 2. Neural mechanisms of language. The second study analyzed how the brain organizes language production. It demonstrated that the brain processes language in a structured, layered manner, beginning with abstract meanings and progressively translating them into specific words and actions. This hierarchical processing mechanism ensures coherent representation of successive words, revealing the complexity of human thought and communication. 3. Challenges and future directions. Although the research indicates a promising path forward, several challenges remain. The current accuracy of 80% leaves room for improvement, in practical application in clinical settings requires overcoming issues related to motion restrictions and the need for specialized environments. Future research will involve exploring the applicability of these findings in patients with brain injuries and further refining the technology to enhance its usability and efficiency. Timeline of events. 2017, Meta first announced its ambitions in brain-computer interfaces, laying the groundwork for future research. 2025, the Fair Lab published two significant research papers detailing the success of decoding brain signals into text and elucidating the neural mechanisms underlying language production. Conclusion. Meta's recent research marks a pivotal advancement in the intersection of AI and neuroscience. The ability to decode human thoughts into text with 80% accuracy opens new avenues for communication technologies that could significantly improve the quality of life for individuals with speech impairments. While practical applications remain on the horizon, the collaboration between AI and neuroscience is poised to transform our understanding of human communication and cognitive processes. For further reading and detailed insights, the full research papers are available on Meta's AI blog and various academic platforms. Meta's recent research breakthroughs in decoding human thoughts into text using non-invasive brain-computer interfaces (BCIs) presents several layers of counterintuitive information. Here are some of the notable aspects. 1. High accuracy amidst limitations. While the technology claims an 80% accuracy rate in decoding thoughts to text, this statistic can be misleading. The reported figure reflects optimal conditions under controlled settings with healthy participants. In practical applications, especially with individuals who have speech impairments or brain injuries, achieving similar accuracy may prove significantly more challenging. The counterintuitive aspect here is that even with advanced technology, the real-world effectiveness may be much lower than indicated by laboratory results. 2. Non-invasiveness versus practicality. The research emphasizes the use of non-invasive techniques like magnetoencephalography (MEG) and electroencephalography (EEG) to record brain activity. However, the practicality of these methods poses a paradox. While non-invasive techniques are less risky and more appealing for clinical use, they require participants to remain completely still in magnetically shielded rooms. This requirement can limit the technology's application, especially since many potential users may not be able to comply due to physical or cognitive constraints. 3. Dynamic neural code complexity. The findings suggest that the brain uses a dynamic neural code to represent successive words and actions, which implies that language processing is a highly integrated and layered process. This contrasts with simpler models of language production where thoughts are converted directly into speech or text. This complexity indicates that understanding human communication may be far more intricate than merely decoding brain signals, suggesting that advances in AI will need to account for these nuanced brain functions. 4. Challenges in broader applications. Although the research points to the potential for aiding individuals with speech loss, the transition from research to clinical application is fraught with challenges. The technology is still in the laboratory phase, and the statement that it could help restore communication for people with speech loss may create a false sense of readiness for clinical deployment. The realization that significant technological and practical hurdles remain before these methods can be widely used is a counterintuitive takeaway. 5. Limited scope of current research. The studies primarily involved healthy volunteers typing sentences. This raises questions about how well the technology would perform with patients who have diverse neurological conditions affecting their cognitive and motor functions. The implication that this technology could be beneficial for a broad range of speech-impaired individuals, without sufficient evidence from actual patient data, is a potentially misleading perspective. 6. Illustration versus application. Meta's research primarily serves as an illustration of what might be possible in the future rather than presenting a definitive step toward practical applications. This focus on theoretical advancements in understanding brain function and language processing may inadvertently downplay the immediate applicability of the technology, highlighting a disconnect between groundbreaking research and real-world utility. 7. Investment versus outcome. Meta's financial commitment, such as the $2.2 million donation to support research, might suggest a robust pathway towards successful product development. However, past experiences in tech development indicate that financial backing does not guarantee successful outcomes, particularly in complex fields like neuroscience. This presents a counterintuitive notion that investment does not directly correlate with technological success. 8. Public perception of brain-computer interfaces. The excitement surrounding the potential of BCIs to decode thoughts could lead to inflated expectations among the public. Many may envision a future where thoughts can be effortlessly translated into text without understanding the intricate challenges involved. This gap between public perception and scientific reality is a crucial counterpoint to the optimistic narrative often presented in media reports. 9. Overemphasis on AI's role. the narrative may overly credit AI's capabilities in bridging the gap between thought and language. While AI plays a role in processing and interpreting data, the complexities of human cognition and communication involve factors beyond algorithmic efficiency. This reductionist view may lead to an underappreciation of the biological and psychological nuances inherent in human thought processes. In summary, while Meta's advancements in brain-computer interface technology are impressive and hold potential for transforming communication for individuals with speech impairments, these developments also reveal counterintuitive truths about the limitations, practical challenges, and broader implications associated with translating human thought into text. As research progresses, it will be essential to navigate these complexities carefully to align expectations with realistic outcomes. Meta's recent announcements regarding their breakthrough research in decoding human thoughts into text with 80% accuracy using non-invasive brain-computer interfaces (BCIs) carry significant implications that many people may overlook. While the headlines may focus on the impressive accuracy and the potential applications for communication restoration, several critical aspects of this research are noteworthy and merit deeper consideration. 1. The nature of collaboration in neuroscience and AI. One of the most important yet overlooked elements of this research is the emphasis on collaboration with established neuroscience institutions. Meta's partnership with the Basque Center on Cognition, Brain and Language and other European research centers underscores the importance of interdisciplinary approaches in scientific advancement. This collaboration not only lends credibility to the research but also facilitates sharing of expertise and resources, which is crucial for tackling complex challenges in understanding human cognition and language processing. Significance. The collaborative nature of this research highlights a broader trend in scientific inquiry, the necessity of interdisciplinary partnerships to achieve breakthroughs. This could inspire future research initiatives across various fields, illustrating that significant advancements in technology often stem from combined efforts among experts in different domains. 2. Insights into language processing mechanisms. The second breakthrough, understanding the neural mechanisms behind how thoughts are transformed into structured language, reveals the brain's hierarchical processing of language. The identification of a dynamic neural code that links successive representations of thoughts is a profound finding that could reshape our understanding of cognitive neuroscience. Significance. This insight is particularly significant for the fields of AI and machine learning, as it could inform the design of more sophisticated neural networks. By understanding how the brain organizes thoughts into coherent language, researchers can develop AI systems that mimic these processes, potentially leading to more advanced natural language processing capabilities. 3. Practical challenges and limitations. Despite the impressive 80% accuracy rate, the research still faces practical challenges that are often glossed over in discussions about its implications. The requirement for participants to remain still in a magnetically shielded room, along with the technology's current inability to be deployed in real-world settings, poses significant limitations to its immediate applicability. Significance. Acknowledging these challenges is critical for setting realistic expectations regarding the technology's deployment. It emphasizes the need for continued research and development before such systems can be widely used, particularly in clinical settings. This understanding can help mitigate potential disappointment or skepticism from the public and stakeholders regarding the timeline for practical applications. 4. Ethical considerations and implications for privacy. As with any technology that involves decoding thoughts or intentions, ethical considerations are paramount. The ability to convert brain activity into text raises questions about privacy, consent, and the potential misuse of such technology. While the research focuses on aiding individuals with speech impairments, the broader implications of thought decoding could lead to ethical dilemmas regarding mental privacy. Significance. As developments in brain-computer interfaces advance, there is a pressing need for discussions around ethical frameworks that govern their use. This includes safeguarding individuals' rights and ensuring that such technologies are used for beneficial purposes rather than invasive surveillance or manipulation. 5. Potential for broader applications beyond speech restoration. While the immediate applications of this research are geared toward individuals with speech impairments, the underlying technology has the potential to extend to other areas such as enhancing human-computer interaction, gaming, and even education. The ability to decode thoughts into text could revolutionize how we interface with technology, allowing for more intuitive and seamless communication. Significance: by recognizing the broader applications of this research, stakeholders can begin to envision a future where human cognition and technology are more closely integrated, potentially transforming industries and everyday life. This forward-thinking perspective can guide further investment and exploration in related technologies. 6. The role of AI in understanding human cognition. Meta's research not only advances technology but also contributes to our understanding of human cognition itself. By utilizing AI to analyze brain signals, researchers can gain insights into the fundamental processes underlying thought and language, which can have far-reaching implications for psychology and cognitive science. Significance: this interplay between AI and cognitive understanding opens avenues for new research questions about the nature of human thought and the potential for artificial systems to replicate or enhance cognitive functions. It encourages a multidisciplinary approach that combines neuroscience, psychology, and AI research, potentially leading to a more comprehensive understanding of intelligence. Conclusion: Meta's breakthrough in decoding human thoughts into text is a remarkable achievement that carries significant implications for various fields. However, the importance of collaboration, insights into language processing, practical challenges, ethical considerations, broader applications, and the integration of AI in understanding cognition are critical aspects that warrant attention. Recognizing these nuanced dimensions of the research can foster a more informed dialogue about its potential and limitations, guiding future developments in brain-computer interfaces and their societal impact. 1. Advancements in non-invasive brain-computer interfaces (BCIs). Meta's research represents a significant leap in the development of non-invasive BCIs, specifically in the ability to decode human thoughts into text with 80% accuracy in real time. The use of magnetoencephalography (MEG) and electroencephalography (EEG) to interpret brain signals offers a less invasive alternative to traditional methods, making it a potential game-changer for individuals with speech impairments such as ALS or traumatic brain injuries. The implications of this technology extend beyond mere communication restoration. It opens avenues for various applications in assistive technologies and cognitive neuroscience. 2. Understanding neural mechanisms of language production. The research provides substantial insights into how the brain processes and structures language. By identifying a dynamic neural code, the studies demonstrate that the brain does not merely process language in a linear fashion but rather utilizes a hierarchical approach where thoughts are transformed into coherent sequences of words. This understanding could lead to improved AI models that emulate human cognitive processes, enhancing the development of more sophisticated language-based AI systems. 3. Collaborative research approach. The successful outcomes of Meta's research underscored the importance of interdisciplinary collaboration in advancing neuroscience and AI. Partnering with institutions like the Basque Center on Cognition, Brain, and Language highlights how collaborative efforts can yield significant breakthroughs. The commitment to open science is also evident as Meta has pledged support for further research initiatives, indicating a long-term investment in understanding the intersection of AI and human cognition. 4. Challenges and limitations in practical application. While the breakthroughs are promising, the research also highlights substantial challenges that remain before the technology can be effectively applied in real-world clinical settings. Limitations include the need for participants to remain still in a magnetically shielded room, the current performance accuracy of the decoding system, and the requirement for further studies to explore its applicability to patients with varying brain injuries. Addressing these challenges will be crucial for translating these advancements into practical solutions for those in need. 1. The case of BrainGate.
The BrainGate project, initiated in the early 2000s, is a pioneering research initiative that aims to develop brain-computer interface (BCI) technology to help individuals with severe motor disabilities regain communication and control over their environment. The project involves implanting microelectrodes into the motor cortex of the brain to capture neural signals related to movement intentions. These signals are translated into commands for external devices such as computer cursors or robotic arms. The research has demonstrated significant successes in allowing paralyzed individuals to control devices through thought alone, leading to enhanced independence and quality of life.
2. The University of California, San Francisco UCSF Brain-Computer Interface Research.
UCSF has conducted groundbreaking research into BCIs, particularly focusing on enabling patients with ALS amyotrophic lateral sclerosis to communicate through thought. In a notable study, researchers implanted electrodes in the brains of individuals with ALS, allowing them to select letters on a screen by simply thinking about moving their fingers. This research has led to the development of systems that can decode complex patterns of brain activity into intelligible speech, significantly improving the communication abilities of patients who have lost the ability to speak.
3. Neuralink's progress in brain-machine interfaces. Founded by Elon Musk, Neuralink is working on advanced brain-machine interfaces with the goal of creating devices that can be implanted in the human brain to facilitate direct communication between the brain and computers. In 2020, Neuralink demonstrated its technology by implanting a device in a pig's brain, allowing it to control a computer interface purely through neural signals. The company aims to develop applications for treating neurological disorders, restoring motor function in paralyzed individuals, and ultimately enhancing human cognitive abilities.
Neuralink's research has sparked significant interest and debate regarding the ethical implications and future capabilities of BCIs. The recent breakthroughs in brain-computer interface BCI technology from Meta have opened up a fascinating and promising frontier in both neuroscience and artificial intelligence. The ability to decode human thoughts into text with an accuracy of 80% in real time is a significant milestone that could reshape communication, particularly for individuals with speech impairments. Looking ahead, several key predictions and outlooks can be made regarding the future of this technology, its applications, and the ethical considerations it raises.
1. Advancements in accuracy and usability.
In the short term, we can expect ongoing research and development efforts aimed at enhancing the accuracy of thought-to-text decoding systems.
While the current 80% accuracy is impressive, further refinements in algorithms, better signal processing techniques,
and more sophisticated neural network architectures could lead to even higher accuracy rates. Innovations in sensor technology and machine learning could also facilitate more seamless user experiences, reducing the need for participants to remain still in controlled environments.
2. Broader clinical applications. As the technology matures, its applications in clinical settings are likely to expand.
Currently focused on aiding individuals with speech loss due to conditions such as ALS or brain injuries, future applications may include rehabilitation therapies for stroke patients and communication aids for individuals with developmental disorders. The integration of BCIs with other assistive technologies could create comprehensive systems that enhance the quality of life for users.
3. Integration into consumer technology.
While the current BCI systems are confined to research labs, advancements may pave the way for consumer-grade devices.
In the next decade,
we could witness the emergence of wearable BCIs that allow for thought-based control of devices similar to smart home technologies, enabling users to interact with their environments using mere thoughts. This could revolutionize how we engage with technology, making interfaces more intuitive and accessible.
4. Enhanced human-machine collaboration.
As machine intelligence continues to evolve, the interplay between human thought processes and AI systems could become more sophisticated.
Future BCIs may not only decode thoughts but also interpret emotions, intentions, and context, leading to more effective human-machine collaboration.
This synergy could enhance productivity in fields requiring creativity and problem solving, as AI could assist in brainstorming or decision making processes by interpreting user thoughts in real time.
5. Ethical and privacy considerations. With the advancement of thought decoding technologies, significant ethical and privacy concerns will arise.
The potential for misuse of such technology, whether through unauthorized access to an individual's thoughts or the manipulation of thoughts, could lead to calls for stringent regulations.
Ethical frameworks will need to be established to protect the rights of individuals using BCIs, ensuring that their mental privacy is safeguarded.
6. Impact on mental health.
Future research may explore the implications of BCIs on mental health. The ability to decode and visualize thoughts could provide new avenues for therapeutic interventions, allowing therapists to understand their patients' thought patterns in unprecedented detail.
However, this capability also raises concerns about the psychological impact of having one's thoughts so intimately analyzed,
necessitating careful consideration and study.
7. Cognitive neuroscience research. The insights gained from decoding human thoughts will likely propel research in cognitive neuroscience forward. Understanding how the brain translates abstract thoughts into structured language will enhance our knowledge of cognitive processes and could inform the design of more advanced AI systems that mimic human reasoning and language abilities. This could lead to significant strides in the development of artificial general intelligence (AGI). 8. From technical hurdles to ethical considerations.
9. Cultural and social implications. The widespread adoption of BCIs could have profound cultural and social implications.
As communication methods evolve, societal norms around privacy, consent, and interpersonal communication may shift. The ability to communicate thoughts directly could lead to new forms of expression and understanding, but it could also challenge existing concepts of individuality and selfhood.
Conclusion. The unveiling of Meta's BCI research marks a significant step toward a future where human thoughts can be translated into text with remarkable accuracy. While the technology is still in its infancy, the potential applications are vast and varied. As we progress, it will be crucial to navigate the ethical landscapes and social ramifications that accompany such powerful technology. The next decade promises to be an exciting period of exploration and innovation at the intersection of neuroscience and artificial intelligence.